Hello, can you see my slide?
Yes.
Okay. Okay, thank you very much for having me. I would like to talk about my recent work in heavy quarkonia production in potential nonrelativistic QCD. This work is done in collaboration with Nora Brambilla and Antonio Vairo in the Technical University of Munich. And this is based on this preprint that came out a few months ago. So here's a brief outline of my talk. I will first go over introducing the inclusive heavy quarkonia production in NRQCD. Then I will present my previous recent work on potential NRQCD formalism for NRQCD matrix elements. Then I will give some phenomenological results for production of POA quarkonium. Then I will conclude. So since we had two nice talks about this whole formalism and this problem, I'll go over this very quickly. Inclusive production cross-sections of heavy quarkonium in colliders are important observables in QCD. And nonrelativistic EFTs, such as NRQCD, provide a factorization formalism for quarkonium production. So this factorization formalism looks like this. So a heavy quarkonium inclusive cross-section is a product of perturbatively calculable QQ bar cross-sections, given here, times the non-perturbative NRQCD matrix elements. And this is summed over possible angular momentum and color states of the QQ bar. These matrix elements are usually determined from measured cross-sections because completely in general, it is not known how to compute them from first principles, with the exception of a class of color singlet matrix elements that can be related to decay matrix elements. So, and so far, this approach has not led to a comprehensive description of measurements, especially when it comes to JSI cross-sections, JSI polarization, JSI momentum distribution in jet, and so on. So what we aim to do here is to actually compute the matrix elements using the potential NRQCD effective field theory, which is obtained by integrating out the scales above MV squared. So potential NRQCD is obtained by integrating out the scales over above MV squared, and that includes the scale MV that appears in NRQCD. And we work in the strong coupling regime where the scale MV squared, which would correspond to the scale of the binding energies, is much smaller than lambda QCD. And this regime is valid for non-Coulombic quarkonia. This would include highly excited states of quarkonia. The degree of freedom of this theory is the singlet field S, which describe the quark and anti-quark at positions x1 and x2 in a color singlet state. And the Lagrangian looks like this, very simple. The pNRQCD Hamiltonian H is obtained by matching to NRQCD, and this is done non-perturbatively, although we do expand in powers of small scales divided by the heavy quark mass M. The equation of motion of this Lagrangian is the Schrödinger equation, just given by this equals 0, which and this gives the wave functions and binding energies and so on. And this formalism provides expressions for decay matrix elements in terms of wave functions at the origin, as is well known from calculations in potential models. And at higher orders in 1/m or for higher dimensional operators, these decay matrix elements can also involve universal Clonic correlators. These are universal in the sense that it does not depend on the labor of the heavy quark nor the radial excitation of the heavy quarkonium state. So since we have a formalism for computing decay matrix elements, we would like to extend the formalism for computing production matrix elements. So what are the differences between production and decay matrix elements? So these have different forms. I have a generic decay matrix element on the right here. Decay matrix elements are expectation values on a heavy quarkonium state cube. The operators are generically 4-quark operators. We have a operator, a Pauli spinner that destroys a heavy quark here, and a Pauli spinner kite dagger, which destroys a heavy anti-quark. And K and K prime are are polynomials of color and spin matrices, and also covariant derivatives. On the other hand, production matrix elements, that looks like this. These are vacuum expectation values of these operators. And we have a projection operator in the middle that projects onto states that quarkonium, that contains a quarkonium plus anything. So not only this operator projects onto a quarkonium state, it also can involve quarkonium plus any light excitations. So in order to compute production matrix elements, we need to identify the projection operator. So to describe how we do that, we briefly review the formalism for computing decay matrix elements in strongly coupled pNRQCD. What we do is expand the NRQCD Hamiltonian and its eigenstates in an expansion in powers of 1/m. So H is the Hamiltonian. These are the eigenstates. N equals 0 corresponds to the ground state. Excited states with n larger than 0 have energy gaps of order lambda QCD. And x1 and x2 are positions of the quark and anti-quark. These positions make sense in the static limit, which is given by the leading order piece in 1/m. Since in strongly coupled NRQCD, excited states with n larger than 0 have energy gaps of order lambda QCD. These are integrated out. So a heavy quarkonium state is just given by the ground state. So this leads to the following master formula for computing decay matrix elements. So we have quarkonium wave functions, a contact term, which is the matching coefficient between NRQCD and pNRQCD. Here R is the relative coordinate and large R is the Sanger mass coordinate. The contact term, this one is proportional to a delta function of the relative coordinate. So this would involve quarkonium wave functions at the origin. And in general, this can also involve derivatives that act on the wave functions and also universal Coulombic correlators. So what do we do about this quarkonium projection operator? This projection operator is essentially a number operator that counts the number of quarkonium in the state so that it destroys any state that does not contain a quarkonium. If we neglect the decay rates, which makes sense within the context of NRQCD, because decay rates that involve momentum transfers of order m are integrated out from NRQCD, and the only remaining decay processes that remain in NRQCD are transitions between heavy quarkonium states, and those occur very slowly and can be neglected compared to the timescale of hadronization of QQ into a quarkonium. So it is to a good approximation, this projection operator and the NRQCD Hamiltonian are simultaneously diagonalizable. Also, the matrix elements of this projection operator should involve this ground state, because this describes a quarkonium in vacuum. But not only that, the matrix elements of this projection operator can also involve higher excited states with n larger than 0 if this describes a quarkonium plus light particles meaning anything that can be produced from light quarks or gluons. So in general, we can write a simultaneous eigenstate of this projection operator and the NRQCD Hamiltonian as a linear combination of these eigenstates with different coordinates. For n equals 0, this is just the Quarkonium state in vacuum. And so phi is the usual Quarkonium wave function. For n larger than 0 for the excited states, the wave functions are in general known. And once we write this state, we can write the projection operator in this simple form. But the sum is restricted to states that reduce to color singlet QQ bar at leading ordering 1 over m, that is the static limit, and at x1 equals x2, that is at the origin, so that the QQ bar actually forms a regular Quarkonium. So we need to know what the wave functions are for these states. Quarkonium wave functions are determined from a Schrödinger equation where the potential is a vacuum expectation value of a Wilson loop. This is the general result in the static limits and also can be extended to higher orders in 1 over m. At leading order in 1 over m, that is the static potential for the ground state. The potential looks like this. This is a Wilson loop with spatial size r and time extension t. The spatial size r comes from the displacement of q from the q bar. We take the vacuum expectation value of it, and by taking the logarithm and taking limit t going to infinity in this form gives you the static potential as first discovered by Ken Wilson. For the potential for the n larger than 0 states, that is the excited states, the light excitations in these states should also be included. So not only we have the Wilson loop, which originates from integrating out the heavy quark and anti-quark fields, but also we have cloning operators represented by this circled X. They represent the light excitations that make up this eigenstate. And we make use of this factorization property of vacuum expectation values of products of color singlet operators that factorize into products of vacuum expectation values of individual operators in the large NC limits. This is valid up to corrections of relative order 1 over NC squared. So the excited potentials reduced to this form. This is factorized into the vacuum expectation value of the Wilson loop times the vacuum expectation values of the cloning operators. And because this is inside a logarithm, we have the static potential of the ground state plus a constant piece that corresponds to this contribution. So this differ from the n equals 0 potential by only a constant. And because the potential differs from the static potential from just a constant, this has no effect to the wave functions. So the wave functions are independent of n, of course, in the large NC limit. And so the projection operator is just given by this simple expression with now these states given by the usual Quarkonium wave functions that we can compute from a Schrödinger equation. So now we can compute the production matrix elements by plugging in the expression we found for the projection operator. So we have this master formula. Now this piece is now the contact term for the production matrix elements. Phi are the usual Quarkonium wave functions. So since the contact term can be computed order by order in 1 over m, This allows calculation of production matrix elements in strongly coupled pNRQCD. And the technology to compute these contact terms are the same as we have done for the decay matrix elements. So now I would like to go over to some phenomenological results. We have applied this formalism for production of P-wave Quarkonium, specifically chi-Cj and chi-Bj. At leading order in V, the cross-section is given by these two channels. There's a color singlet channel that corresponds to production of a QQ bar pair in color singlet state with in a spin triplet and P-wave state. And there's a piece contributing at same order in V that corresponds to production of a QQ bar in a color octet state with spin triplet and in an S wave. The color singlet operator looks like this. There's a covariant derivative in each of the QQ bar operators on each side. And the color octet operator looks like this. There's a color matrix on each side between the quark and anti-quark operators. And there is also a Wilson line connecting from the position of the QQ bar operator here to infinity in the L direction, which is necessary to ensure the gauge invariance of this operator, which has been pointed out by Nayak, Chu, Sturman back in 2005. So we compute both the color singlet and color octet matrix elements in strongly coupled pNRQCD. So what we get for the color singlet matrix element is we reproduce the known results that has been obtained in the vacuum saturation approximation, which equates the color singlet production operator matrix element to the color singlet decay matrix element. And this is just given by a square of the radial wave function at the origin. It's the first derivative because this is the wave function for the P-wave state times some color factors. When we calculate the color octet matrix element, the result is given in terms of the wave function, just like the color singlet operator matrix element. We have the same factor here, the wave function, the radial wave function at the origin, times a universal Volony correlator E. The definition will be given in the next slide, times some color factors, and we pull out the factor of heavy quark mass. So this E is a universal quantity that does not depend on quark flavor or radial excitation. So determination of this non-perturbative quantity directly leads to determination of all chi-Cj and chi-Bj cross-sections, as well as HC and HP production rates through heavy quark spin symmetry. So this Volony correlator E is a dimensionless quantity defined in terms of chromoelectric fields. I write as G times E, inserted at times T and T prime, with Wilson lines phi extending to infinity in the L direction. We first have to go to the origin in the temporal direction, then go on to infinity in the L direction. And we take the first moment of this vacuum expectation value. This correlator has a one-loop scale dependence that can be easily verified by calculating this in perturbative QCD. The result looks like this. And this is consistent with the evolution equation for NRQCD matrix elements, which is given in this form. We can simply plug in this one-loop scale dependence to these formulas to reproduce this evolution equation. In principle, this E can be determined from lattice QCD, but since that has not been done yet, we determine this quantity from measured chi-CJ cross-section ratios to obtain this number. And based on this determination, we can calculate all sorts of cross-sections of P-wave Quarkonium. We first show you the cross-section ratio of chi-C2 versus chi-C1 at the LHC compared to ATLAS and CMS data. Our results are shown in this orange band. The agreement is very good. We can also calculate the wave function at the origin and calculate the absolute cross-sections. These are chi-C2 and chi-C1 cross-sections at the LHC compared to ATLAS data. Again, the agreement is very good. We have obtained the wave functions at the origin from 2-photon decay rates of chi-C2 and chi-C0. We can also do polarization with by calculating polarized cross-sections, polarized Q-bar cross-sections. So this is chi-C2 and chi-C1 polarization at the LHC, shown by this point with error bars. And this is compared to the experimental constraints from CMS, given by this band. We can also do bottomonium with the same gluonic correlator. We first show the cross-section ratio of chi-B2 versus chi-B1 of the 1p states at the LHC compared to LHCb and CMS measurements. Again, the agreement is very good. We can also calculate the production rates of chi-Bj 1p, 2p, and 3p by calculating the chi-Bj wave functions at the origin. We calculate them from averages of a number of potential models in the market. What we show is the chi-Bj production rates relative to the epsilon cross-sections at the LHC, because there's a measurement of feed-down fractions by the LHCb collaboration. This is computed by this formula. We have a ratio of chi-Bj and epsilon cross-sections multiplied by branching ratios of chi-Bj going to epsilon. Again, the agreement is pretty good, with the exception of the 1p to 1s feed-down fraction. That is possibly because the 1p is probably too close to the ground state. That's the assumption that it is strongly coupled may not be so valid. So this brings to my summary. We have developed a formalism for computing inclusive production of heavy quarkonium in strongly coupled potential NRQCD. And for the first time, first principles determination of color octet production matrix elements may become possible by computing those universal gluonic correlators. And in the case of P-wave Quarkonium production, a single gluonic correlator leads to determination of all of P-wave charmonium and bottomonium cross-sections, and most of them are in good agreements with LHC measurements. So this formalism can also be applied to S-wave Quarkonium, such as J psi, eta C, epsilon, and eta B, and may even be extended for calculating exotic states. And finally, lattice determinations of these gluonic correlators are desirable because without them, we still need to rely on extracting them from data. Thank you, that is all.